In Chapter 4, you're going to be asked to graph a function using calculus. So you're not going to be allowed to use any kind of graphing technology like a graphing calculator or Desmos. Those will not be allowed on Test 2. You have to show supporting calculus work that leads to the construction of the graph. Now, the good news is you're only going to be asked to graph polynomials. Those are nice, smooth curves. The domain is always all real numbers. You will not be asked to graph a rational function that would have holes or asymptotes or things like that. You won't be asked to graph a logarithmic function or an exponential. You'll only be asked to graph polynomial functions. So you will have some algebra knowledge that you can use to kind of check your work and see if your graph is making sense. You'll know the basic shape of the graph based on the degree of the function. You'll know whether the graph opens up or down if the ends point the same direction, based on the leading coefficient and the degree of the polynomial. There'll be some algebra knowledge you have, but you need to use calculus to support the graph. And that calculus is called the 4-step graphing strategy. So I have those 4 steps outlined in your notes here. The first step is just straight up algebra. You're just going to analyze the function that was given to you. You're going to think about the domain and the intercepts. That's the y-intercept and the x-intercept. You're going to think about all that. Those are important points on the graph. But that's just algebra. There was no calculus happening there. For step 2, you're going to create a first derivative sign chart. Remember, that first derivative sign chart is going to tell us the local extrema of the original f of x graph, and it's also going to describe the slopes of the tangent lines on the graph of f of x. Then for your next step, you're going to create the second derivative sign chart. The second derivative describes the concavity of the original f of x graph. And then the fourth step is just to put all that information together to create the graph of f of x. So let's see that in action on question number 10. Okay, step 1, this is the algebra step. We know the domain of a polynomial is all real numbers, and we need to find the intercepts. Let's start with the x-intercept or intercepts. There might be more than one. To find that, we need to find inputs that make the output of the function equal to 0. Well, we have the function rule, so I just need to set that equal to 0 and solve for x. In this case, I have a binomial. There's a GCF of x cubed, so I can factor out that x cubed GCF, and then I can use my zero product principle. So either x cubed is equal to 0 or the binomial x minus 4 is equal to 0. So x cubed equals to 0 if x is a 0. You get cube root both sides if you didn't see that using mental math. And then for the binomial, if I add 4 to both sides, I'll see that x minus 4 equals 0 if x is equal to 4. So there are 2 x-intercepts here. If I input a 0 into my function, I'll get a 0 output. And if I input a 4 into the function, I'll get a 0 output. So we have 2 x-intercepts. Okay, one at the point 0, 0. The input was 0 and the output was 0. And the other x-intercept is at the point 4, 0. If I input a 4, I output a 0. Okay, now we need to find the y-intercept. That's the easier one. We just input x equals 0 because remember, if you're on your y-axis, that y-intercept is going to cross the y-axis when x is 0, right? X is 0, we just have to find the height of that y-intercept. And there's only one y-intercept. Because we have a function, it has to pass the vertical line test. So this one's the easy one. We just input a 0 into our function rule. So I have input to the 4th power minus 4 times the input cubed. And if I input zeros, I get 0. And I know that just because we already found that x-intercept. If the x-intercept's at the origin, that's also your y-intercept. So yeah, we just have one y-intercept, and that's going to happen at the origin 0, 0. Okay, so we finished step 1. So now we move on to step 2. Now the calculus starts because step 2 tells us we need to create the first derivative sign chart. So I went ahead and I used my power rule to find my first derivative. And now we need to find the partition numbers of the first derivative sign chart. To do that, I need to set the first derivative equal to 0. I mean, technically a partition number could also occur when the first derivative is undefined, but again, we're dealing with a polynomial function, which is defined everywhere for all real numbers. So I'm just going to set my derivative rule equal to 0. And again, I'll factor out a GCF. In this case, it's going to be 4x squared. That'll leave me an x minus 3 binomial factor. And if I set 4x squared equal to 0, that's only going to happen if x is equal to 0. And if I set the binomial x minus 3 equal to 0, that's only going to happen if x is a positive 3. So those are our partition numbers. So I'll go ahead and put those on my first derivative sign chart. I'll be sure to label this sign chart with an F prime. I'll put my inputs there as my partition numbers. Above those partition numbers, I'm going to put zeros because they created an output of 0, a derivative of 0. And then you need to do your test points. Okay, so I picked some test points in each of those intervals, and I can see that my outputs go from negative, then they hit 0, stay negative, and they hit 0, and then the outputs go positive. And make sure when you pick those test points that you're plugging them in to the first derivative function rule, because we're creating a sign chart for the first derivative. Okay, so this first derivative sign chart is going to describe the slopes of the tangent lines of the original function, and it's also going to tell us about any local extrema on the graph of f of x. Well, let's look at these partition numbers. At both partition numbers, I hit a horizontal tangent line because the derivatives are 0 at those partition numbers. So I have a horizontal tangent line when x equals 0, but my tangent lines were going negative, then they hit 0 and go negative again. So that would look something like this. Okay, my tangent lines will point down, they'll hit 0, it'll go horizontal for a split second, then they'll continue to point down. So there's no local extrema when x is equal to 0. There's not a min or a max there, but there is a horizontal tangent line. But at the next partition number, I can see that my tangent lines were going down, they hit 0, the tangent line goes horizontal when x is equal to 3, and then the tangent lines point back up. So I do have a local min at x equals 3. So I'll keep that in mind when I go to sketch my graph. Okay, now on to step 3. Okay, now it's time to create the second derivative sign chart. So I'm going to take the first derivative, which was 4x cubed minus 12x squared, and use the power rule to find the derivative of f prime. So that'll give me 12x squared minus 24x. Okay, and again, to find the partition numbers, I need to set that equal to 0. It will never be undefined because it's a polynomial, but it will be equal to 0. I'll factor out my GCF. In this case, that's going to be a 12x, so that'll leave me with an x minus 2 binomial factor. And using my zero product principle, 12x will equal to 0 if x is equal to 0, and the binomial x minus 2 will equal to 0 if x is equal to positive 2. So those will be the numbers on my sign chart. I need to make sure I label this sign chart as f double prime of x. Okay, so 0 and 2 are my partition numbers, and I'll write zeros above those partition numbers. So now we just need to do our test points. Okay, selected some test points in each of the 3 regions. My first test point was x equals -1, and again, make sure you are plugging it into your second derivative rule. When I did that, I got a positive output, so that region has plus signs above it. When I tested x equals 1, I got a negative output, so that region is marked with negative symbols. And when I tested x equals 3, I got a positive output, so that region is represented with positive symbols. That means I go from concave up to concave down, and then I change again to concave up. So we have 2 inflection points. When x equals 0, my concavity changes from concave up to concave down. That makes x equals 0 an inflection point. That's where my concavity changes. And then my other inflection point is at x equals 2. Okay, my concavity changes at x equals 2. So that's step 3. Now we just need to put all those steps together and create a graph of f of x. So I'm going to come over here. This is step 4, putting it all together. I'm going to label my y-axis as f of x because we're graphing the original function. I have some information from step 1. I have some x-intercepts and some y-intercepts. So what was that? Where were those? Okay, so I had 2 x-intercepts at the origin and at the point 4, 0. And the origin was also my y-intercept. So let me label those. So my origin is a point on the graph, and 1, 2, 3, 4. The point 4, 0 is an x-intercept. Okay. And the domain was all real numbers, so I know I won't have any holes or asymptotes or anything. Now we're going to go to step 2. That was our first derivative sign chart. That was right up here. And did we have any local extrema? We did. We have a local min at x equals 3. So when x equals 3, I need to align a local min with that partition number, with that input. And since we have the function rule, we can locate the exact height of that local min by plugging the input x equals 3 back into the original function. Remember, f of x gives us all the points on the graph of f. So if I plug 3 into the original function, that's going to locate the height of that local min. So let's do that. Oh, wow, that's going to give us a negative 27. So my local min is located way down at 3, negative 27. Okay, so this isn't going to be drawn to scale here, but I'm going to come way down here. I have a horizontal tangent line at that point, and that point has a local, that's my local min, so I'm going to label that. It's a local min, and I'm going to write the ordered pair since my graph isn't drawn to scale there. Now, the other partition number on that sign chart, x equals 0, well, that has to be the origin 0, 0. That was neither a max nor a min, but we did have a horizontal tangent line there. So I am going to draw a horizontal tangent line through that point. Okay, so that was the information I got from the first derivative sign chart. I can also use this sign chart information in a minute. Oops. Thought I had my highlight tool to just check the slopes of the tangent lines after I draw my graph. But right now I'm just going to mark those local extrema. Okay, and now I'll use my second derivative sign chart to label, to locate any of the inflection points and then draw the shape of my graph. So my first inflection point was when x equals 0. Again, that has to be at the origin. We've already calculated the output when x equals 0, 0, 0. So that's going to be an inflection point, but I need to locate this inflection point when x is a 2. So let's go ahead and do that. I'll just plug 2 into the original function. Okay, so I'm going to put, I'm going to put 2 into my original function now. So that'll give me 2 to the 4th minus 4 times 2 cubed. Okay, and that gives us negative 16. Okay, so we've located that other inflection point. The inflection point is going to occur at 2, negative 16. So I'll go to 2 on my x-axis, and I'm just going to eyeball somewhere in here. We're going to label that to make it really clear that this is my inflection point, and it's occurring at 2, negative 16. Okay. And again, we have another inflection point up here, but that one's at the origin. And then I just need to connect this using my concavity. So I'm going to start concave up until I hit x equals 0. So I'm going to make sure I really emphasize that horizontal tangent line, but the rest of that graph is going to be concave up. And then I'm going to move to concave down until I hit x equals 2. So concave down there, and at 2 I go down to 16. So this shape there is going to be concave down. And then once I hit x equals 2, I go back concave up. I'm at another inflection point. I'm going to hit that local min and bounce back up. Oh, don't forget to go through that other x-intercept. So I need to make sure when I come back up, when I bounce off that local min, I'm going to bounce up through that